right, we might get started. I'll just start with a quick acknowledgement of country. So first of all, the University of Queensland would like to acknowledge the traditional custodians of the land from which we meet today, or wherever you are and live and work. We pay our respects to their ancestors and their descendants who continue cultural and spiritual connections to country. We recognise their valuable contributions to Australian and global society. So thanks everyone for coming, and thanks to those online for joining. So today we're lucky enough to have Max, who's a climate physicist / environmental economist from Germany, working on the impacts of climate conditions on socioeconomic systems. But he's going to be talking about his work that he's doing here at the University of Queensland, which is more biodiversity focused. So if you hold your questions for the end, we'll have some time for questions and a discussion for Max. Take it away, Max, over to you.
Great, thanks very much, Brooke. Thanks everyone for joining. I think you might need to click Brooke onto the presentation, and then I can change the slides. Cool, great, yeah. So as Brooke mentioned, I'm Max. I'm from Germany, working at the Potsdam Institute for Climate Impact Research, naturally on climate change topics. And yeah, while I've been here for the last couple of months, I've been actually visiting the economics department, but I've taken the opportunity to come and spend time at CBCS to learn a little bit about conservation, biodiversity, and try and get some collaborations off the ground with regards to assessing the impacts of climate change on biodiversity, which is what I'm going to be talking about today. I've been doing some of this work with Tatsuya Amano and James Watson from in the department here. And it's fairly preliminary work. We've been doing it just the last couple months, but we've got some interesting results that I think are worth sharing with you. So very much looking forward to trying to get some feedback on that. Good, so the broad context and motivation for the work is one of which I'm sure you're all well aware, that we're facing a global state of biodiversity decline. Pick your metric, Living Planet Index in terms of population abundances, or species extinction risk. Both of them paint this pretty dire picture of declining biodiversity. And faced with this kind of challenge, it's pretty important for us as a scientific community to try and understand the different drivers of biodiversity decline. And to start to look a little bit into that, I just wanted to take a recent example from IUCN, from a report they published quite recently in the last year, looking specifically at species extinction risk for amphibians. And so it's really just an insight into their sort of expert elicitation of what has driven the different extinction risk for these different species. And this particular figure is showing what they've evaluated over this period, 1980 to 2004, and then over the last 20 years. And we can see sort of some of the expected culprits, let's say, of disease, habitat loss, degradation, overexploitation. But in particular, what's notable in the change between this first 20-year and the second 20-year period is the increasing relevance of climate change effects for extinction risk for amphibians. So for someone who's interested in climate change like myself, this is like a really interesting thing to start to see, and really is sort of giving an indication of this fact that climate change is becoming increasingly relevant for biodiversity and extinction risk, which is sort of borne out in some other contexts as well. So when starting to think about like climate change, biodiversity, and extinction risk, personally, I think it's quite good to try and get some quite broad context from the geological record. So in Earth's like geological history, we've had loads of different extinction events, often like referred to as mass extinction events, and often they've been associated with large changes in the global climate. So this is from a study a couple of years ago, which I think just explains this really nicely, or just shows it really nicely. Just plotting the extinction rates in these different extinction periods, global extinction rates, against changes in global temperatures and rates of change in global temperatures over those periods. And you can see this very simple but quite clear relationship, such that periods with faster changing climatic conditions and larger changes in climatic conditions have had larger extinction rates. And in particular, the big 5 mass extinctions in the geological period, they're all of those that fall at this quadrant of the scale where there's really high, rapid rates of change in global temperatures. And in particular, quite worryingly, if we look at, say, the climatic change that we've actually experienced historically, we've had about 1 degree increase in global temperatures over about the last 100 years. And if we convert that into the scale that they've got here for these geological events, which is degrees per million years, that puts us at about 10,000 degrees centigrade per million years, which is like 2 orders of magnitude off the x-axis here in terms of what's actually happening today. So it's these really unprecedented global changes in climatic conditions. and at the end of the scale where we really know it's likely to be associated with large-scale mass extinction events. Cool, so bringing this back to a more sort of modern perspective, what can we try and do, or what do people typically think might be the responses of species populations to changing climatic conditions, and how do people go about trying to assess that in a modern context? I just wanted to give an outline of sort of 3 potential responses of populations, like species populations, to climate change that are typically discussed in the literature. On the one hand, we could think that species might move to try to follow the set of environmental and climatic conditions that they find most preferable, so sort of following a climatic niche. On the other hand, if they're not able to do that, we might think that they might adapt locally. And if they're not able to do either of those things, we might expect them to undergo some kind of decline or potential extinction. And one of the most common methods that's used to try and assess potential impacts of climate change on biodiversity is these species distribution models, which I assume you're probably all much more familiar with than me. And what these will typically do is they'll take a set of like environmental covariates, typically describing like long-term climatic conditions, and try and predict the occurrence of certain species depending on those conditions. And then they can use that model to look under future climatic change, when the future conditions change in a certain way, how species distributions may change. And so when sort of looking into this method, we can sort of see that it's essentially based on this first idea of how populations might respond, that they're going to track the climatic conditions that they find preferable, and that's going to be a good predictor of how they change. And that is borne out in certain cases, that does seem to be the case. But it's really only one of the possible responses. And I also think that it's just interesting to note that there's a couple of limitations, as far as I can see, with using these kind of species distribution models, which I just want to point out. The first of which is that they don't exploit the historical data that we actually have on how species abundance has changed historically, how populations have actually changed in the historical period in response to changing conditions. And also I mentioned that they typically build their models based on like long-term average environmental conditions, long-term climatic conditions. And those kind of things, they're really unlikely to adequately reflect the potential impacts from extremes, climatic extremes that occur over much shorter timescales. So it's a really powerful tool, these species distribution models, but it's potentially a little bit limited in representing some of these things that could be important. So just to dwell on this role of climate extremes, I just want to give 2 examples to emphasize why they might be important. They're things, again, you're probably very familiar with, or at least aware of. The first being marine heat waves. So this is like from a simple study that's sort of like counting the number of days per year in which sea surface temperatures have exceeded a certain critical threshold that meets the criteria for marine heat wave. This is the sort of map of what that looks like in terms of those increases spatially. And they're overlaying it with species richness to look at like which areas of global biodiversity are actually threatened by these types of events. And again, these marine heat waves, they're events that occur over sort of like weekly to monthly timescales. So they're much shorter timescales than these long-term average conditions, and these kind of species distribution models are probably unlikely to reflect impacts from these events well. But we know from some other studies that they can have really big impacts. If we look at, say, for example, the Great Barrier Reef, there's been like really serious alterations to marine ecosystem structures in response to these kind of short-term events. And similarly, we could look at land, we could look at wildfires. There's a study from CBCS from a few years ago looking at the impact of the 2019 to 2020 megafires on Australian fauna habitats. You can see these really dramatic declines in available habitat for certain species. And again, these kind of events, they're ones that occur over shorter timescales than what you're likely to be able to capture when looking at these long-term conditions. Okay, so what could we try to potentially do to look at this in a slightly different way? Like I said, these species distribution models, I think they're great in many ways, but they might lack the ability to detect certain impacts, to describe certain impacts. And I'm going to describe in this talk something that we've been doing over the last couple of months to try and provide a different approach. And what we're going to do is we're going to use historical data on species abundance from the Living Planet database, specifically vertebrate species abundance. So we've got then time series of local populations of a given species and how that's changed through time. And we're then going to use climatic data to assess how those populations have been exposed to certain extreme climate conditions, and again, get like a nice time series component of that. And we're then going to combine these in some models, some empirical models, to try and assess how changes in these climatic conditions may have plausibly impacted species abundance in a plausibly causal kind of framework. Great, so to start with our data, this is what the available data we have from the Living Planet database is. I don't know if you work with it, maybe you do, so you're probably familiar in that case. What I'm doing, and for the whole of the study really, is I'm going to be grouping species into these kind of categories, quite broad categories, based on their species class and then their habitat system. So we've got data here for the terrestrial birds and the freshwater birds. You can see the distribution of the populations where we have observations there on the left, and then terrestrial mammals, freshwater fish, and terrestrial reptiles. And there's decent coverage, like across most continents, but it's heavily biased, obviously, towards like Europe, towards North America, Australia, which we can talk about maybe some of the implications of that a bit later. But it's good, we've got time series for each of these locations for a particular species, and we're then going to try and define how these species populations have been exposed to climatic conditions, and in particular trying to look into climate extremes. So I'm just using some climate data here, which is sort of the state-of-the-art go-to historical climate data that one might use. It's sort of combined product that's taken satellite-derived and ground-based temperature and precipitation metrics and put them together into a sort of best assessment of what the state of temperature and precipitation was across the world at 0.25 degree resolution every day over this very long period. So it's quite nice to use in this kind of global sense. And we're going to define extreme metrics for each population locally, essentially by taking the 99th percentile of the daily distribution of temperature and precipitation at each specific location. And that's what these maps are showing you. This is like the 99th percentile of daily temperature and precipitation over the 1940 to 1970 period, actually. So this early historical period. And then every year for each population, say we've got a species that lives here in India, a particular population, we're going to count how many days in that year did it experience conditions that exceeded these high thresholds. And that's just going to give us a very simple metric of their annual exposure to temperature or heavy precipitation extremes. Cool, and then we're going to put these into models together to try and estimate how these climatic conditions have impacted species population abundance growth rates. And this, what we're going to use here, it's kind of like it's a mixed effects linear modeling framework, which is very common in the climate impact literature. We'd call it like a fixed effects panel regression model, but in the more like biostatistics world, you might call it like a mixed effects model with a random intercept and fixed slopes. Yeah, so we're trying to model the population growth rates in logarithmic form for these different populations. We're allowing it to depend on the size of the population in the previous year. So there's this sort of like Gompert style growth model. And then we're putting in different climatic conditions here as a predictor. We're going to use a variety of climatic conditions and then see what's sort of important. And we have this this population level fixed effect, which really just sort of like removes any time invariant differences between populations, and it really allows us to focus on the fluctuations across time, which is really this dimension in which we can have a more, I would argue, plausibly causal interpretation of the kind of regression coefficients that we then identify. But there are some other sort of important time-varying factors that we might want to take into account. So, for example, human pressures, which are obviously changing through time, obviously going to be a potential predictor of how species populations are changing or declining. So I use sort of like a simplified version of the human footprint. It's not the full version, because to do that, you need a lot of complex data, which isn't really available across the whole historical time period that I'm looking at. So I'm just using one that's based on human population density and land use change using the HIDE Global Environment Database over the last 100 years. And then that sits in there as like a nice sort of control variable and additional predictor. Okay, cool. So this is really the framework that we've got to work with. We've got our time series data on species population abundance. We've got assessments of climate conditions, not just these extremes, but I'm also going to look into changes in average conditions. Also the extremes, and then also a drought metric, and we are controlling for changes in the human footprint. And I'm going to try and build empirical models for each of these groups so that we can have an aggregate response of, say, the terrestrial mammals, the terrestrial birds. So it's quite high level, but we're going to include interaction terms such that there can be a different response of populations based on their latitude. A lot of previous work suggests that there's different responses, say, at the tropics compared to the high northern latitudes, and also dependent on the extent of human pressure in that area. Great, so we can start to look into some results, and this first thing is really horrible, and I don't want to actually really look into this and try and understand it. I'll show it to you in a much nicer format in a second. That's just to give you an indication that what we really do is we build a model for each of these different species class habitat systems, including a bunch of potential climatic conditions as covariates, each with interaction terms to allow them to have different effects. And then we just select the ones that are significant. We drop terms that don't seem to have an important effect. So it's kind of like a semi-systematic scan to look for potential impacts. But yeah, there's probably better ways we could do this, but this is what we're doing at the moment. And if we then want to start to look into what those responses actually mean, I tried to put it into a more nice graphic format for you all. So for each species class habitat system combination, for example, the freshwater fish, we build a model that's going to be looking at the response of its population growth rates to a number of different climatic conditions, including the annual average temperature, annual precipitation, the temperature and the precipitation extremes, and also a drought metric. And on the y-axis of each of these boxes is going to be showing just the response of the population growth rate to a given increase in one of these variables. Now, if there's like a dependence on the x-axis, that's because we've had an interaction term. That means that the effect can vary across this interaction term, so in this case, across the absolute latitude. And if we look into this sort of upper left quadrant, what this is showing us is the impact of annual average temperature on freshwater fish growth rates. And we can see that there's this statistically significant negative impact at low latitudes, but it's contrasted by a positive impact at high latitudes. Yeah. So there's strong latitudinal dependence. We don't find any significant impacts of precipitation changes, but we do find some negative impacts of temperature and precipitation extremes, as well as droughts at low latitudes. Yeah. So it's quite a complex picture, and I'm going to go through this for each of these different combinations of species class habitat systems, but we'll revisit these as well to sort of get more of a broad sense of what they mean as we go. So next we're going to look at, say, the freshwater fish, yeah? And by and large, we see like a general positive response to increasing temperatures for this is freshwater birds, not freshwater fish, this is actually, maybe you might think it's surprising, but it's quite consistent with some of the pre-existing literature that they can actually benefit from these kind of temperature increases. Also see benefits from increasing annual precipitation, negative impacts from daily precipitation extremes, but actually positive impacts from temperature extremes and some mixed response to droughts. The terrestrial birds are quite an interesting case where we don't see any impact at all of the average conditions, but we see a strong negative impact of daily temperature extremes, which is much more negative at lower latitudes. And we also see some additional impacts of precipitation extremes and also droughts. And this is just showing you the number of observations we have for each of these different models. And then when we look at the terrestrial mammals, we see it's a bit of a confusing mixed response that I need to still get a bit of a grip on, but there's seemingly negative significant impacts at low latitudes as well. So you can see that for the temperature impacts, there's quite this clear dependence on latitude for their magnitude and direction. But then some different impacts where there's actually seemingly positive impacts of daily temperature extremes and heavy precipitation extremes, and some mixed response to droughts. Whereas the reptiles, we've really not got very much data, and it's kind of very hard to say anything at all. So I'm not going to speak about the reptiles anymore after this. But the main picture that I want you to take away from this is that there's quite a lot of detail of things going on here, but we can see clear impacts of historical changes in climatic conditions on these different species abundance that really vary across the different types of species, really vary across the different habitat types, and also vary across different locations. Particularly, there's a strong latitudinal dependence of the temperature impacts that we see. Okay, so that's a good starting place for us, where we can see that there are some different impacts of climatic conditions on population growth rates in this historical period. But a natural question that might arise after that is, what are the actual implications of these empirical models under climate change? Yeah. So we know that over the historical period, we've already seen pretty much a 1 degree increase in global temperatures. So we might want to ask, what have been the implications of that for species abundance, given the empirical models where we've seen these actual effects playing out. So this starts to be a bit of essentially an attribution question in a climate change terminology. So I'm going to take you through like a simple climate change technique that we might use to do this kind of attribution. Essentially, we're trying to attribute changes in local climate conditions to human influence, to anthropogenic influence. And we're going to do that in two kind of simple stages. The first of which is sort of assuming that changes in global temperatures are attributable to human influence. And we can assume that pretty well because it's backed up by very, very broad scientific consensus. You can look into the IPCC reports that really show that all of the observed warming that we've had historically is pretty much a combination of these three. Well, this is the total human influence, and this is two separate human influences. So pretty much everything we've seen is a combination of the human influences, not from these natural drivers. So this is our first statement. We know that global temperatures are being caused by humans. That's one thing we can take for granted. So given that, what we can try and do is then say, well, how are the local climatic conditions, for example, the local extremes, how are they related to global temperatures? How are they changing in response to global temperatures? And as a result of that, we can build this kind of two-step attribution process. Okay, so to do the second part, we take quite a simple approach where we just take the local changes in climate conditions for a given population. So this could be the average temperature, it could be the temperature extremes. And we do a simple time series linear regression against global temperature changes. And this will essentially then give us the changes in this local temperatures that we think are actually attributable to the global climatic change and hence also to human influence because of these two-step attribution process. And once we have this, we essentially have time series for each population that tell us how the local climatic conditions have changed in that location because of human influence, yeah? And what we can then, this is just me citing some literature that sort of introduced this approach. But yeah, having got this attributable change in local climatic conditions, we can then combine it with the impact parameters that we get from our regression models, which describe how changing climatic conditions impact species abundance, then to get ourselves an attributable change in the population growth rate of the local population, which we can say is being caused by human influence. Yeah, so it's quite a complicated sort of step of procedures. So I hope that was clear. If there's something there that you didn't follow, feel free to ask now, actually. But just to make sure it's still awake. But each step is fairly simple. It's just like a simple regression, and it's based on these fairly well-justified assumptions that global temperature change is connected to human activity. These local conditions are connected to global temperature change. And then we can combine it with the results from our empirical model that says this is how species respond to the changing conditions. Good, so once we've got this, we can then put it on top of, or sort of combine it with the data we already have from the Living Planet database to try and assess how have populations actually changed in their overall abundance because of climate change, yeah? That's what this term can essentially give us when combined with the Living Planet database. And I'm going to start to show you some of the results of what this then looks like. So what we're showing here is the results for the freshwater fish, and these are the different populations where we have at least 5 years of data, so it's been restricted a little bit. And what I'm showing you in color here is the changes in the historical populations, which we think are attributable to anthropogenic influence because of the climate change that's happened over this 1940 to 2020 period. And you can see that there's this clear latitudinal dependence, such that there's strong negative impacts at low latitudes that are up to about 40% reduction in population numbers, but there's strong positive impacts at high latitudes, which again reach up to about 40%. If we look into what's actually driving those changes, we can look back to the empirical model that we built for these freshwater fish. And remember that I mentioned that there's this strong latitudinal dependence of the temperature response for the fish populations. And if we look at, this is sort of breaking down these overall impacts into these different climatic conditions, and we can see that this spatial pattern is really being driven by the average temperature changes, which ends up causing this overall pattern of attributable impacts. But in addition, the temperature extremes are contributing overall negative impacts as well as these precipitation extremes and some mixed impacts from drought. Similarly, we can look at the terrestrial birds, which shows quite an interesting picture. Similarly, with this latitudinal pattern, strong negative impacts at low latitudes and some negative impacts at higher latitudes of smaller magnitude. And again, this is really being driven by the temperature response, but in this case, mainly the temperature extremes, which is where we saw significant impacts in our empirical models. If we then look into some of the other species groups, particularly the freshwater birds and the terrestrial mammals, we see broadly positive responses. And these are really being driven by their positive responses to general temperature changes, or in the case of the mammals, temperature extremes, which is one that I find a little bit harder to sort of reconcile or understand at the moment. But quite interestingly, there are strong negative impacts in the Australian region, which are really being driven by increasing drought, decreasing precipitation totals in our analysis. Cool, so we can start to sort of come towards some kind of conclusions, and I want to just talk about some of the main limitations that I think we have in this study. I think a big one is this geographic and taxonomic bias that we have with the Living Planet database. And at the moment, I'm assessing things at a very sort of global aggregate level. So you can really see this geographic bias in all of these maps that I've shown you, where we've got lots of data at these high latitudes, very little data across the low latitudes. So if we wanted to, for example, try and say what's been the overall global impact, and we just took an average, it would be quite sort of biased towards these high latitudes where we see positive impacts compared to these low latitudes where we see negative impacts. So it'd be good to think about ways we could try and improve that. But also there's potential taxonomic bias. I'm doing these models at this very aggregate level of species class, so for the whole of the mammals, the whole of the freshwater birds, terrestrial birds, and assuming that they all have essentially the same response in my modeling framework. The fact that we see some statistically significant effects means that, okay, we can start at that level, but obviously there's going to be bias, and it could be interesting to try and look into more specific genus or family level responses, depending on how the data allows, depending on what data is available. Cool, but having said that, I think we can draw out some general conclusions that this work seems to have been able to draw out. First of all, I think what's most important to emphasize is that it indicates that climate change has already had attributable impacts on historical species abundance, which have fairly large magnitudes when we look at this, like up to sort of 40% is fairly substantial. And in addition, when we break down what's driving those impacts, we can see that climate extremes are playing an important role, sometimes sort of an equal role, but in some cases, like the terrestrial birds, for example, it's those increases in temperature and precipitation extremes that are really driving these impacts, and not changes in average conditions in that case. And I think that just really emphasizes that we need to sort of take into account these kind of extreme events, these short-term changes that aren't necessarily well represented by species distribution models, for example. And finally, as I alluded to when talking about the terrestrial birds, these impacts, they vary a lot depending on the species class we're looking at, depending on the habitat system we're looking at, and also depending on the geography. Like, for example, this strong latitudinal dependence that we seem to see quite repeatedly. And I think that's quite interesting. It kind of calls for us to try and look in more detail into these specific responses, try and understand how these different populations are responding. Great, so with that, I'm going to conclude and just say a quick thanks to CBCS, who've been very welcoming over the last couple of months. I wasn't affiliated with CBS at all when coming here. I just sort of snuck my way in and I managed to go to Heron and like come to a lot of talks, and people have just been really friendly, so I really appreciate that. If you want to get in touch, you can do so these ways. But yeah, looking forward to some questions if there are any. I'm sure, like I don't have a background in ecology at all, so I've probably made a bunch of like terrible assumptions. So I look forward to hearing what those might be. And yeah, like I said, it's an early stage, so it's good to get some feedback now. So thanks very much.
Thank you, Max. Are there any questions for Max from the room, first of all? Oh, yeah.
Sorry, I have a question about the resolution of the data within Planet Index, which I should be on top of. So yeah, do you have estimates of abundance for each species year on year? 1 year after 1 year after 1 year? Like consecutive years, basically.
Yeah, so in some cases, yes, you have consecutive years. We restrict ourselves to cases where we have consecutive years because we look at this year-on-year growth rate. Yeah. So then we're only looking at that case. But there is a big caveat to some stuff I've done that I just sort of skipped over, more for time than for anything else. Yeah. Which is that there are big gaps in the database. Obviously, there's not 1940 to 2020 in that database. Some have like 10 years here, some have 20 years there. So one thing that we do in order to come up with these overall assessments, which is very, very simple, but probably problematic, is we just take like we extrapolate based on the 10 years or 20 years of available data that we have, like a log linear relationship, assuming the population is just going to have continued growing at that same rate over this historical period. And then we add our climate impacts on top of that. So I need to look into this as to how sensitive our overall results are to those assumptions. My intuition is that they're not very sensitive because we're still looking actually at percentage impact. And this is really just a way for us to get over data availability issues in a sort of reasonable way. And
so a population that is at some sort of carrying capacity, for example, can be expected to continue growing in relatively stable conditions over, like depending on the length of that. That might be something to consider.
Yeah, that's interesting because we have in our empirical models we have this sort of like Gompertz growth style term, which I guess
right. So that has
this should try and capture that to some extent. And when I do the extrapolation of the data, I don't account for that. But when I add the climate impacts in, I do account for that. So I say that, okay, if we think that climate change has made them bigger than they would have been, well, they also then would have grown slower based on how we see in the empirical model. So there's already kind of an adaptation element sort of built in there to these results that I showed.
And a follow-up question, if I may. For several of the tests, you got negative effects of extreme temperature events on population growth. Do they rebound?
Good question. Yeah, that's a good question. That's not something we've looked into, but it's something that we could do by sort of using these like lagged structure of an analysis. Okay, is that something you would expect to see?
I don't know what my expectations are, but I think it would be valuable
to look at. Yeah, cool.
Because you're just looking at population growth over a single year, right?
Yeah.
For each event or each
each exposure
interval of average conditions.
Yeah.
And so I guess the cumulative effect on abundance over time isn't currently captured by your analysis. You're just getting like your response variable is 1 year of growth, your independent variables of what's happening within that year.
Yeah.
And so any sort of cumulative effects aren't allowed.
Yeah, good point. Yeah. Okay, no, it's very good feedback. So yeah. And you think would a good way to take that into account be using, say, like a lagged model where you have like a number of, you look at, say, this is the response of population growth in year Y to temperature in the previous year and the few years previously, and then you might see, if there is a rebound, let's say, then you might see a negative impact for your first lag,
you might get,
and then a positive rebound.
Maybe you could continue to get negative. Like I don't know, working a little bit on heat waves, and there is some evidence to suggest that, you know, if you get hit by one and then hit by another, you just keep going. So cool, but I guess that would be in some ways taking into account some sort of correlation.
Yeah, cool, great. Yeah.
Really interesting work, fantastic presentation. And just curious on we're looking at extreme events and various different events, and is there any say interactions or cumulative or compound type of event they're looking at? Say, for example, remember one of the things is the heat waves or heat conditions, and as well as drought, and if this could be a compound effect or after another, and some interactions between those.
No, really good question. The drought index that we use is one that's kind of a composite index constructed from both temperature and precipitation. It's the typical way that they use to sort of measure droughts. That would be to some extent accounting for these different conditions together. Well, it depends. So if we're thinking about like potential compounding impacts, in the empirical models that we construct, we use the different climate variables at the same time. So if there's 1 year where they both have a temperature extreme and a precipitation extreme, we'll see them both having an effect, but we don't account for any sort of additional marginal effect because of the fact they occur together, which is, I guess, that's what a compounding effect would be indicating. I've not looked into trying to do things like that. That would actually be something I guess we could try. I guess it would sort of be on this sort of like second level of detail almost, because it's already like there's quite a lot of, like with these models already, we've got quite a lot of different terms, let's say all these different climate variables, their different interactions. If we want to then start to look into the potential rebound dynamics, then we have more lagged terms. So it depends what we're able to do in terms of the data, but I think that's quite an interesting question of like, compound.
Yeah, like something like a model from the rebound.
Yeah.
Rebound is when there is a good year and then there's and bad years, and then there's with a few good years, and then there's potential rebound.
Yeah.
The compound is probably the consecutive bad years and of different type of event. Push it to even further.
Yeah. No, I see what you mean. Yeah, it starts to get complicated, doesn't it? In terms of then you have to sort of take into account the time series structure of when these events occurred, which you could do. Just it'll get much more complicated. But it's good. And people are talking about that a lot in terms of like climate change impacts in general, the idea of compounding events, and like they're quite closely related questions in some sense, because like you say, like if you have one, then you have another, then you really expect the dynamic response to be quite different in terms of a potential rebound or compounding negative impacts. So good things to think about for me.
I guess I've got maybe potentially a dumb question. Most of my experience with like climate change and vertical declines comes from like elevation and sort of the elevator to extinction theory, where certain animals will be dependent on certain elevation bands basically, and they can only go so far to capture change? Have you thought about looking at any other sort of variables like elevation that might soak up certain noise and like say, okay, well, this species has declined here because of an extreme heat event? That's only because it actually now can't go any further. So
Yeah, really
change, something like that.
Yeah, no, super interesting. That's something we can actually do quite straightforwardly. I mean, at the moment we have this interaction term with latitude, and you could very easily put in one with elevation as well, actually, which is quite interesting.
I think on that point, there was one of the maps you had up here. It might be the next slide.
Yeah.
It was, I'm pretty sure, birds with
Terrestrial birds?
temperatures. Yeah.
Yeah.
There was a blue dot in northern South America, right there in the Andes in Ecuador.
Yeah. Yeah.
That's the first thing I thought of was the elevation. There
Yeah.
could be elevational change.
Also on Ayers Rock in Bill Australia.
Again, because these are kind of built from global models, it's kind of hard to be like that's not going to be representing that local population's response to temperature. It's going to be representing the overall response then evaluated at that location. So it's hard to know whether that's then being driven by a potential elevation effect. But
I mean, the reason I thought about that is if you look at like the wet tropics, there you've got a decline in birds, and that is the elevator to extinction, that they can't physically go anywhere else to escape those extreme temperature events. So I just wondered whether that would maybe help soak up some of the pattern and explain it more broadly, but that could also be bullshit. So
you mean so like if they're at the top of a mountain range, yeah, they're trying to move away from the temperature because they literally just can't move anywhere. Yeah, sure. Yeah, no, we could do that with an elevation term quite straightforwardly actually.
Good luck to fish.
Sorry?
So good luck to fish.
Yeah, maybe depth. I don't know, depth. Sorry, but it's like just swim downstream. Yeah.
We've got a couple of questions in the chat. So the first one's from Lily. Predictably, she has a bird question. She wants to know which types of species of bird fell into the freshwater birds group.
Oh, I can't tell you, Lily. I'm so sorry. It really just depends on what happened. Categorized it in the Living Planet database, and I didn't look into that. I'm really sorry. I can try and follow up and share some information with you. But yeah, that's where my interest or my expertise in the ecological questions comes to an end. And I was like, okay, I'll try and do this first, and then those details we can draw out.
She says no problem. The next question is from Frankie. So, okay, I'm being Frankie.
Yeah.
I think this piece of work has the potential to inform larger scale models that link anthropogenic climate change to its economic damages and its associated damage functions that relate temperature changes to loss in economic productivity. So with modeling species, one aspect is that these species move and do not stay in the same location when exposed to climate effects. Thus, with climate extremes, you might see decreases in abundance in climate extreme affected areas, but increases in abundance in areas not affected by it because of species movement.
Yeah.
Are you actively thinking about these potential movements and develop a more general model that encapsulates these tricky ecological dynamics?
Super good question. Love it. No, at the moment, but I can talk about something interesting in another context where we're thinking about really similar questions. I think, yeah, I mean, I think even in this kind of case, it's well, not for the freshwater fish, but because they can't move, can they? But for the terrestrial birds, like if you see, say, like positive impacts at these high latitudes and strong negative ones at the low latitudes, your intuition when looking at it on a map is like, okay, they're just like, maybe they're just moving. The difficult thing in this context is like, this is representing different species that we don't know. It's the same species here as it is there. We're also not tracking their movements. So we can't really say about whether they are going locally extinct in terms of like dying or whether they're moving. We can't say anything about that. And currently there's I'm not using an empirical framework that tries to say, okay, we have a climate shock here at lower latitude. Is that then inducing an impact somewhere else that's correlated to that rather than the other way around? I've not started doing that here, but I've got a good collaboration going on at my institute at home where we're doing a very similar sort of type of study in terms of the method, but looking at human migration patterns. And it's really interesting. You see really similar, you see quite similar patterns. You essentially see when you have like extreme weather events or strong temperature shocks at low latitudes, you get reductions, you get people leaving those regions essentially. And you see people going to higher going to regions at higher latitudes. I was really surprised that we were actually able to see this. And in that context, we were actually able to connect temperature shocks in one location to changes in migration or sort of immigration in another region. But to do that, the way we were able to construct that is because we have historical data on the flows of migration from one region to another. So we can say that, okay, in Germany, we know that historically 80% of migrants have come from like Vietnam and Thailand and 20% from Russia or whatever. So we can make a statistic that estimates the climate exposure in these locations that aren't Germany, but that we think should be connected to Germany via migration. And then we can start to assess that. In this context with the species, we don't really have, at least I don't have any good a priori information about like where a species is likely to go and therefore which location I should try to assess in terms of climatic impacts to then see if it has gone there. Maybe if we, I don't know, there is data on like migratory routes of birds. I don't know, that could then get very complicated as well, and I don't know how well it would actually match up with the availability of living planet data, but potentially that could be a way to try to do something similar. So Frankie, yeah, maybe Frankie, if he has a follow-up, because that's quite an interesting question.
He says, yes, absolutely. Studies on the human adaptation to climate change through migration could potentially inform on your study as well. Would be great to connect these approaches in economics with ecology.
Yeah, so the economics question is interesting too, because I mean, just for context, like this type of study as well is something I've done a lot in the context of predicting impacts on economic, socioeconomic outcomes, like using similar types of models, similar kind of frameworks. And is Frankie meaning then that in terms of like, if we have an impact on, say, some aspect of biodiversity, then that we can evaluate its ecosystem value or function for the economy, and then use that to inform economic damages? Is that what Frankie means? Maybe you can type a response quickly. I don't know.
Is that what you mean, Frankie? You said, yeah, potentially.
Yeah, cool. Yeah, nice.
Tricky to do, I think so.
Yeah. There's a question from here in the room as well, so.
Yeah, I was just thinking like as a baseline, because especially those like upper latitudinal positive shifts do seem like it could be like a latitudinal displacement. So is there potential with the living planet database to do like assess changes in species composition over time as well, so you're capturing whether there's like local extinction that's being sort of drowned out by either like influxes or like the reproductive success of invasive species or
Yeah, well, I mean, so the availability of data, what they really have is just number of species in a given location at like a lat long point.
Yeah.
So if you then was like aggregate these into some kind of broader area, I don't know what would be appropriate, but like some 50 kilometer scale or something, then you could get some sense of, okay, what's the assemblage, what's the different species that are present in some location. But then I guess it's just difficult because there's such a big measurement bias in terms of who's been measured, what's been measured, that it's kind of hard then to, I think it's maybe easier to make statements about the overall potential impacts rather than like what the specific species assemblage impacts might be, because I think that's probably more sensitive to the measurement bias than the just general impacts. But there are other things out there. There's other databases like there's this predicts database, which is maybe more focused on like assemblage composition and stuff, which I thought about looking at actually as well to begin with, but didn't, because it didn't have such a good like clear EC time series component to it. But definitely with this broad type of approach, I think you could try and answer those questions depending if you had the right data. Yeah. Thanks for the question.
There's a question from Jaden. He said, also a predictable question from me. Does the data on marine heat wave extremes consider deeper ocean waters? Thinking about the abyssal plain.
I don't think so. I think normally these kind of studies that look at marine heat waves, they focus on, I'm not going to go all the way back to the slide, you sort of remember it, but they're focused on the surface and like maybe some of the water column, just because, as you tell me repeatedly, Jaden, that's where most of the species are actually living. That could be interesting to try and assess some of these deep water temperature changes, because there are actually big shifts going on in the deep water structure as well, largely because of circulation changes as well as just like direct warming. And yeah, like I don't know what it is, like 80% of the heat from global warming has gone into the oceans rather than the atmosphere. So that's an interesting question. But I also think it's a bit of a problem because measurements of deep ocean temperatures are pretty hard compared to like sea surface temperatures they can get from satellites. So then you have like a decent record. Deep ocean temperatures, you need to be out on a boat, like chucking stuff down really deep, and then they might not have good enough stuff to define these short-term extremes based on those kind of data. But I'm not sure, but yeah, you should look into it if you're interested.
All right. Is there any other questions from the room? I have a question. No one else? I wanted to know, Max, does your findings, do they help then inform on how you might develop better SDMs? Is that the ultimate goal?
I haven't thought about it in that way. I haven't thought about like trying to build a better SDM, but for me it was more maybe like just developing a complementary method to assess their potential impacts. But I guess I mean this sort of insight, let's say that climate extremes have a role, I guess that potentially could be used to try and inform species distribution models, because you can define the exposure to climate extremes at like an annual timescale that you might need for a species distribution model, let's say. But I think in this case, it's more these like year-to-year fluctuations in that exposure, which is driving the potential impacts. Whereas when you look at a species distribution model, you're looking at like, what's the spatial variation in these long-term conditions that predicts abundance. So I don't know whether the exposure to extremes across a spatial extent would be a helpful predictor of occurrence. I'm not really, I'm not sure. So I don't know how directly these could be fitted into, say, a species distribution model. I've thought of them more as like a complementary sort of approach for assessing potential impacts.
Okay.
Yeah.
There is some spatial variation in the predicted locations of extremes. So you could potentially marry some sort of like a heat map, no pun intended, but basically a heat map of the likelihood of extremes. And I might expect stronger effects on species distributions for species whose distributions overlap with areas more prone to different kinds of extreme events. It could be worth looking at as well.
Have you, it's sort of like your work, have you started thinking about how to account for extremes in your modeling work?
Yeah, mine, but this I did quite a really fine scale, and it's down to hourly stuff. So
Oh wow.
But also so some of the work that previously used the same model that I'm using, they use the era 5 to splice to really downscale the whole climate extreme, but they didn't look at specific event, but they look at the whole range, and then the event by itself is artificially defined event, right? But it is a definition of things. But then when you look at the physiological fitness, you will just account through the whole predictions throughout the time, and there's an hourly changes. The event itself embedded within that process. The process based.
So you're looking at impacts of koalas, like this, okay. And using like a time series component as well, or
Time series component, downscale, regional 10 kilometer climate forecast to hourly 9 kilometers climate weather condition to forecast the physiological response.
Okay.
See how's the stability gonna be like. So,
Cool. I was also wondering, so the Living Planet database, you're saying that might be the best database for time series. Did you look at like GBIF?
I don't know what GBIF is. No, so anything else you've got that's I don't know about that might be helpful. Yeah, I'm very happy to hear about.
I guess the problem with GBIF being fur abundance, because GBIF is just people reporting stuff like naturalists and things like that. It's sort of get into the weeds of Well, how do you turn that into a measure of abundance?
Yeah, exactly.
Does map of life have an abundance under here, map of life? Yeah. I don't know if there's any budget there, I'm not sure.
The ones I considered was this, biotime, and the predicts database.
Yeah, the ones.
And this was sort of like felt like the easiest starting place
Okay.
in terms of working with it. I think there's also, like we've spoken a little bit, James mentioned that there's like different databases, like regional databases, for example, like in Australia, for Australian birds, there's like maybe particular other data that isn't represented in here that it could try to do some more region specific studies of a similar nature. Yeah.
Excellent. Are there any other questions for Max in the room or on the chat? No? If that's it, we might call it there. So thank you very much again, Max. We'll give him another round.